Good morning, good day, everyone. Let's start our meeting. Today we have presentation by Dr. Duncan McKay with the title Impact of an L5 magnetograph on non-potential solar global magnetic field modeling. And Dr. Duncan McKay received his degrees from famous University of St. Andrews in 94 and correspondingly 97. He got early career Flower Prize in 2007. His appointment with University of St. Andrews. He has a number of services in national and international committees. And his research interests are computational MHD, code development, solid prominences, coronal heating, magnetic flux, transport simulation, magnetofrictional relaxation models, stellar magnetic fields, sun's open magnetic flux, and solar terrestrial environment. So now we're happy to have this presentation, so please have your 40-45 minutes. I will warn you 5 minutes before. Thank you. Go ahead.
Excellent. Well, thank you for the introduction there, Gregory. So today I'm going to discuss a theoretical study that I've carried out where I consider how an L5 magnetograph could increase our understanding of the non-potential solar corona. So for the talk today, the talk is officially split into 3 separate parts. To begin with, I'll give a very basic overview and introduction where I discuss a little bit about space weather and why the L5 point is important for that. I'll talk a little bit in more detail about one of the solar phenomena that can lead to extreme space weather events, so coronal mass ejections, and then I'll discuss a little bit about a possible L5 space weather mission. Now, this mission has gone by a number of different names. Sometimes people call it Carrington, other times Lagrange, but effectively I'll just call it an L5 mission for the purpose of today's talk. Moving on to part 2, I'll then discuss the construction of global non-potential simulations on the Sun and the technique that we use to do that. That will then naturally lead into part 3 of the talk, which will be the majority of the talk, where I consider how an L5 magnetograph will improve our understanding of the solar corona and the non-potential nature. Now, in order to do this, I need to carry out 3 separate simulations. The first of these is what I'm going to call the reference sun simulation, and that's where we try and use the model to reproduce to the best of our approximation at the present time what the real sun is doing. This assumes that we've got full surface coverage of magnetic fields. After that, I will then construct 2 what I call limited field of view simulations, one from the L1 field of view, which we presently have, but one from a combined L1 plus L5. And what I want to see is how much more accurate is this L1 plus L5 simulation in producing the reference sun model compared to the L1 only. Finally, I'll just give a summary of the results and then discuss some future studies. Now, all the results that I'm going to talk about today have already been published, and it was a paper back in 2016 where this was a study between myself, Anthony Yates from Durham University, and Francois Bocou, who at the time was at the UK Met Office. So just moving on to space weather. Well, space weather really is a name that describes a lot of different phenomena, and it describes the wide range of phenomena that can occur on the Sun, but correspondingly have consequences at the Earth. So we've got a schematic here just showing the variety of phenomena at the Sun and then effect at the Earth, but the table at the bottom sort of links these objects together, such as things such as solar flares, can lead to ionization within the sun's atmosphere, the Earth's atmosphere, and radio blackouts. Coronal mass ejections, these can produce really extreme space weather events at the Earth, such as geomagnetic storms, ground-induced currents, which of course can short out power supplies, and also it can affect GPS. Now, when we consider the effect at Earth from solar flares and CMEs, we're looking more at extreme space weather events. But of course, space weather is always round about us. We have space weather created things just by the EUV irradiance, which is a bit more passive, but also the sun's open magnetic flux and correspondingly the solar wind that escapes from it. The open flux generates or leads to the IMF field, which surrounds the Earth Earth, and of course directly impacts on our magnetosphere and generally impacts us every day. Of course, another solar origin, solar energetic particles, it's extremely important to understand them, as these events, of course, can damage things such as the electronics and satellites, and also danger to manned space missions. Now,
I'm getting voice dropouts.
Sorry? Sorry, I didn't quite catch that. Are you still getting me?
Hugh, what was the problem? We cannot hear you. What did you say?
Am I okay to continue?
Yeah, please go ahead. If Hugh will reappear these questions, we will enter.
Okay. So there's not enough time for me to discuss in detail all these space weather phenomena in cause of Earth, but what I would recommend that people do in order to get more information on this is to consider the paper by Shriver et al. 2015, which gives a very good overview of space weather and how it can affect the Earth. So one of the objects, of course, which can lead to extreme space weather events are coronal mass ejections. So these are just large-scale ejections of mass and magnetic flux from the sun. On the movie in the bottom left-hand side, you can just see an example of a CME taken by Core-2. CMEs can have a wide range of speeds, as much as 3,000 kilometers per second. It can have a mass on the order of 1.6 times 10 to the 12 kilograms, and sort of the mean transit time to get to the Earth is in the order of 3 days. But the importance about CMEs is they can cause extreme space weather events. If we consider the movie just at the bottom right-hand side, we can see the direct interaction between the sun and the Earth through a CME by an excellent movie that was produced by Jackie Davis at RAL Space. So we see the sun at the right-hand side, the Earth here, the small dot at the left-hand side, and by running this movie, we can see the propagation of a CME there, right the way through into planetary space, and then correspondingly impacting on Earth. Now, no matter which theory you like in order to explain CMEs, one of the most important results from, or one of the basic understandings of CMEs is, of course, CMEs originate from non-potential fields on the sun. So if we want to be able to understand or predict CMEs, we have to have a good understanding of non-potential fields. So we need to understand where the free energy is stored in the corona, why it is stored at that location, and also understand the electric current systems. So in order to give us a better understanding of space weather, it has been proposed to launch a satellite and place it at the L5 point. And this satellite would be an operational space weather mission. Now, I'm not directly involved with the agencies that are currently looking into this. However, I can give you an overview of what this mission would entail. But I do recommend that you look at the relevant agencies that are doing formal studies in order to get the most up-to-date information. And I've given a couple web links there. So the key thing is that if we consider the Sun-Earth system, then there are 5 Lagrange points where we see a balance of the gravity between the Sun and the Earth. And of course, the most common one of these that people know about is the L1 point, which exists between the Earth and the Sun. And of course, that's where the SOHO satellite orbited around. We have the L2 behind the Earth, L3 behind the Sun. But most importantly, for studying the interaction of the Sun with the Earth, there are the L4 and L5 points. Now, each of these points are displaced 60 degrees from the Earth, L4, 60 degrees in front of our orbit, L5, 60 degrees behind. But the importance of the L5 point is, of course, due to the direction of rotation of the Sun. This gives us early warning of active regions on the Sun and magnetic activity that is occurring on the Sun as it is coming around towards us. And this 60 degrees equates to about 5 or 6 days earlier warning than what we get currently from our present L1 field of view. Now, in terms of an L5 mission, there is a wide range of possible instruments that could be placed on such a satellite. And again, I would say look at the various working group pages to get more information. However, these instruments can be split up into 2 main types, either remote sensing instruments or in situ instruments. In terms of remote sensing, we would want something like a coronagraph or a heliospheric imager, such as the movie that we already saw. An EUV imager would be extremely useful, as that allows us to image the structure of the corona, see the non-potential coronal loops within it to understand the energy state of the corona. But the thing that's I'm most interested in is having a magnetograph placed at the L5 point. So if we consider the bottom right-hand image, we just see an NSO Solis magnetograph image where white represents positive magnetic fields and black represents negative magnetic fields. Now, the key thing is that when we observe the sun from our L1 field of view, we can only accurately measure active regions or magnetic fields up to about 60 degrees off of central meridian. So you can see these two active regions are bordering on 60 degrees of central meridian. We are able to image them well, understand the magnetic flux within them, and so on. In contrast to that, though, once you get beyond 60 to 70 degrees, such as for the active region at the bottom, you get a lot of foreshortening. You can't accurately measure it. So if you're wanting to run global models to understand the energy state of the solar corona, you can't incorporate these active regions in, even if you know that they exist, basically because you don't know their full properties. But of course, if we had an L5 viewpoint looking in from 60 degrees behind the Earth, then we would be able to image these active regions to a high degree of accuracy and then include them in models. So what I want to do today is determine how much increase in accuracy we would get if we had these L5 observations in the theoretical models. Now, of course, that is the remote sensing instruments. Of course, there'd be a number of in situ measurements as well, things such as a magnetometer or plasma instruments. So the key questions I'm going to ask today is, if we have an L5 magnetograph, can it improve our understanding of the global non-potential fields on the sun? And if it does improve our understanding, how much of an improvement can we expect? Is it just a 10% improvement, or do we get a 40 or 50% improvement in our understanding? So that now moves me on to the second part of the talk, and this is where I'm going to discuss the global non-potential model that I'm going to use in order to carry out this study. Now, for this global non-potential model, this is a model that I've worked on with other people over many years, for nearly 20 years now, where we've aimed to carry out long-term continuous simulations of the sun's large-scale magnetic field. We will generally start off with a potential field configuration. We will then run the simulation forward in time, but after that, the coronal field is non-potential throughout its entire evolution. Now, with this code, we want to be able to study these long-term continuous simulation over periods of months to years and study the build-up of free magnetic energy and helicity in the sun as new flux emerges at low latitudes and is then transported towards the poles. So the movie on the top right-hand side shows an illustration of the model in action just over a 6-month period. And this model contains two separate coupled components. For the first component within the model, we have a photospheric magnetic flux transport model. This simulates the evolution of the radial magnetic field of the sun. It simulates how surface motion shears up the fields and therefore results in an energy and Poynting flux going into the corona. But in order to make sure that our simulations are accurate, within the flux transport model, we also need to include the process of magnetic flux emergence. I'll describe how we do that and also how we can include non-potential dipole emergences within the simulations. Now, as the surface field's evolving, it's injecting energy and Poynting flux into the corona and non-potentiality into the corona. And of course, we need to consider how the corona is going to respond to this. Now, the standard way of doing this would, of course, just be to carry out an MHD simulation, but due to the Alfvén speed time step constraint, it's impossible really to carry out global MHD simulations of the sun over periods of months to years. So what we have to do in the coronal model is use a magnetofrictional relaxation technique instead, where we use a reduced MHD form. So what we're going to do here is, as the surface field evolves, this then evolves the coronal field through a series of quasi-static nonlinear force-free states based on the surface motions that we are applying. And effectively then, through that, we can study the buildup of energy and non-potentiality in the corona. So a key result that we find within these simulations, and this is illustrated by the bottom movie, is that as we shear up the dipoles under these surface motions, what you find is that we generate non-potential fields within the corona volume, in particular along polarity inversion lines. Of course, these are the types of locations that solar filaments and filament channels would form, and we find that we see the build-up of these axial fields and non-potential fields along the polarity inversion lines. Then eventually, within the model, a situation of non-equilibrium can occur, where there is no longer an equilibrium solution to converge to. At that point, then we find and get ejections of magnetic flux ropes within these simulations. Of course, the same sort of idea that Terry Forbes and a number of other people have worked on over a number of years. Now, the development of this model has been carried out over a long period of time. Initially, in a paper in 2000, Ad van Bollehuim, Eric Priest and myself, and then later years, myself and Ad, and then most recently, Anthony Yates from Durham University has also been strongly involved in the development of this model. So just in a little bit more detail about how the model works. So in terms of this model, we'll consider the large-scale evolution, but we'll just consider the evolution through the magnetic induction equation, where we express the magnetic field in terms of the vector potential A, and effectively what we're going to be doing is solving the uncurled form of the induction equation. Now, for the photospheric boundary condition, to describe the evolution of the radial magnetic field, we specify, of course, the variation of the horizontal components of the vector potential, but we include three main flows within the surface evolution. The first of those are differential rotation, so basically the equator rotating faster than the poles, where we use the observed profile. It is a timescale of roughly a quarter of a year. The second motion that we'll consider is meridional flow. So this is a weak flow that acts from the equator to the poles in each hemisphere. It is the order of about 11 to 15 meters per second, and it acts on a time scale of approximately 2 years. Now, the final motion that we include is representing the process of surface diffusion. Now, of course, on the sun, we've got many convective cells. These convective cells lead to a random walk of the magnetic elements, which over larger spatial scales can be represented as a diffusive process. So to simulate the large field, we include the surface diffusion, which of course globally is a timescale of 34 years. So you see that differential rotation is extremely important. It is one of the fastest acting processes that we're going to consider. So the key element is that within this model, these surface...
May I ask, what value for diffusion coefficient?
The value that we use is anywhere from 450 to 600 kilometers per second, but the value we used most recently is 450. Now, the person that worked mostly on this was Rick DeVore, who was at NRL at the time, but now at NASA Goddard. And that's the sort of range of values he determined by comparing simulations to observations. Yeah. Does that answer your question?
It's nothing to do with Spitzer diffusion or something like that, yeah?
No. This is us represent, so it's to do with the convective overturning time, the production of convective cells, granules and supergranules, and then the dispersal of these cells and the dispersal of the magnetic flux. But over larger scales, we can just regard that as a random walk process and a diffusion process.
Okay.
Yep. Excellent. So the key thing is that for the surface model, everything I've described to you is designed to shear up the surface field. This injects energy, non-potentiality to the corona, and of course that is done on a physical timescale. In terms of the coronal model, as I say, we use this reduced MHD form for magnetofrictional relaxation. So the key aspect is that the velocity in the corona is set proportional to Lorentz force. So if you look at the image at the bottom, if we start off with a field line that's initially in equilibrium, we apply a surface motion to that, the field line becomes curved, and then when the field line becomes curved, it can have a non-zero Lorentz force. So the key thing that we're doing here is that we're saying the velocity in the corona is going to be proportional to the Lorentz force, related to by this frictional coefficient, which is designed to aid relaxation of the field. And then in the direction in which the force is acting, the field lines will evolve till they return back to an equilibrium structure. So that's the basic idea between this code, is that we have a series of successions of shearing, relaxation, back to equilibrium, shearing, relaxation, back to equilibrium, and so on. But we also include a number of other features within the corona. We also have a radial outflow velocity that just acts at the source surface in order to simulate the effect of the solar wind, opening up field lines. This has really no effect below about 2.2 solar radii. And in addition to that, though, as well as solving the uncurled form induction equation, we can have the sort of ideal terms given by the means of frictional relaxation process, but also we can have non-ideal terms, and we've got a choice of using either things like eta J diffusion as a non-ideal term, or hyperdiffusion, which conserves magnetic helicity during magnetic reconnection. For the simulations I'm going to show today, they're all carried out within the ideal framework, so we don't use any of these non-ideal terms. So the key thing here, though, you need to notice is that while the surface motions are done in a real physical time scale, in terms of the coronal relaxation, that of course is done over coronal relaxation time scale, which is not physical. So you need to keep that in mind. So one key part of this model is, in order to simulate the solar cycle very accurately, we need to include the process of flux emergence. And when you want to consider continuous simulations and track magnetic connectivity, the evolution of the fields from low to high latitudes, it's extremely difficult to include this process of flux emergence. You don't just have to include it at the photosphere, but you also need to include it within the solar corona. So within this model, we've developed a technique where we can emerge isolated magnetic dipoles which contain either zero self-helicity or positive or negative magnetic helicity. Now, anytime we emerge these dipoles, there will always be a mutual helicity with the surrounding fields, but sometimes you can either have a zero or non-zero self-helicity. To give an illustration of how this occurs, in the image on the left-hand side, we just see an initial coronal state of a pre-existing field, where around about the area where my cursor is, on the next day, we're going to see the emergence of a new magnetic dipole. So what we do when the emergence is to occur is that we switch off the main simulation features, we switch off the surface flux transport model and so on. We determine the size of the dipole that we're adding, and we consider a spherical dome. And then within that spherical dome, we push out all the magnetic fields. So we have a divergent radial outflow in that dome where we generate then a region of magnetic vacuum. This is to simulate the effect of, say, new emerging fluxes pushing pre-existing flux out of the way. We then add the new dipole in at the surface and in the corona, but initially the dipole will not be connected to the other surrounding corona. It will only be connected between its own positive and negative elements. A current sheet will exist around this new dipole, which then will then dissipate quite quickly when we start the simulation up again. The dipole then reconnects with its surroundings and then forms connections to it. So you can see from this dipole, which has newly been inserted, you can see low down the field lines are sheared. So this was actually a dipole which contained a positive helicity component to it, positive self-helicity. Now, the importance of this technique is that it allows us to remain or maintain the pre-existing coronal connectivity and magnetic helicity during the process of emergence, but also the emergence process is carried out as a local process. You can see that around the surroundings, the emergence of this dipole hasn't affected the general larger scale coronal field, but really it's only affected the local field round about it. So I'll just skip over this slide very quickly, as many of these results I've talked about in the past. This is just to show how we've used this model in the past and the variety of usages of it. So to begin with, we've considered this model to try and explain the hemispheric pattern of filament chirality. So in this image here, you see the dark structures which represent solar filaments. They're known to have dextral chirality in the north, sinistral in the south. Dextral chirality indicates negative magnetic helicity, sinistral chirality positive. The image on the right-hand side just shows a one-to-one comparison between the simulation, which ran continuously over a 6-month period with filament chirality, where blue means we obtained the correct chirality, red means we obtained the wrong chirality. So as you can see, the model was good at building up the correct chirality at the correct locations, the model was good at generating the correct helicity at the correct locations in order to explain these solar filaments. It was also applied to consider the sun's open magnetic flux. Now, in the graph on the right-hand side, the thin grey line, which is solid, denotes the IMF field strength taken from Omni measurements, whereas the dashed line denotes potential field model approximations to this open flux. And as you can see, the potential field models generally underestimate the amount of open flux from the sun. The solid black line represents a simulation where we started off with an initial potential field, and then we ran the simulation forward continuously under all these surface effects and measured the amount of open flux. So you can see that over a period of about two solar rotations. So on the timescale of differential rotation, you saw a large increase in the amount of open flux till it was at a level consistent with that found in the Omni data. So the final application, or another application was done. This was a paper done by Anthony Yates by himself, where he studied the solar corona over a long period of time. He measured the amount of fluxural projections within a simulation and then compared that to the ejection rate found in the CDAW catalogue. Now, while the model produced the general overall trend that was found within the CDAW catalogue, what you find is that it only produced about a third of the number of ejections that the CDAW catalogue attained. Now, while this might seem like a low number, there are many models that can explain CMEs going from things like ideal instabilities and so on. So I would never expect fluxural projections to be the sole answer for CMEs. And I think getting a rate of about a third was a very good result that Anthony obtained in the study. So what you're seeing here is that the model has been used to consider a lot of phenomena which occur within the global corona and also a lot of non-potential phenomena. So this now makes me move on to the key element of today's talk, where I'm now going to consider the L5 simulations. And I want to consider, if we have L5 observations, how much more accurate is our understanding of the solar corona? So in order to do this, I'm going to be running three 22-year-long simulations, three non-potential simulations, each over 2 solar cycles. Now, the first simulation I'm going to run, I'm going to call this the reference sun simulation. And in particular, what I'm going to say this is the best representation that the model could produce to what is happening in the real sun at its present stage of development. So it's going to be a 22-year-long, 3-dimensional nonlinear force-free field simulation. But for this simulation, we're going to pretend that we have a full 360-degree magnetograph coverage of the sun. Now, we do this by generating idealized bipole data sets where we can have the emergence of the bipoles at any longitude in the sun at any time, but determined through statistical rules. This reference sun data set, that will then produce the base data set that we want to try and reproduce when we only have a limited field of view. So that moves me on to the next two types of simulations that I will look at, and these are the limited data simulations, where I consider what would happen if we only have an L1 field of view, which is the present case, or if we have a combined L1 plus L5 field of view. So on the bottom two images, we just see how restricted this field of view is. So we have the full surface magnetic field, just shown by this sort of magnetogram image. The dashed line about 180 degrees on each image represents the central meridian in the sun on that day, but the left and right-hand side dashed lines in each image represent the limited field of view where we would be able to make accurate magnetic field measurements. So these are the locations that we could measure the properties of magnetic fields of the sun, insert these properties into a global model, and evolve them forward in time to understand the non-potential state of the corona. So for the L1 field of view, that is just plus and minus 60 degrees either side of central meridian. So we only have 120 degree width of the sun at any one time that we can accurately measure. In contrast, though, if we consider L1 plus L5, we've got a further 60 degrees behind the present orbit of the Earth, monitoring the surface of the sun. So now we have a full 180 degrees that we can make accurate measurements from. So what we want to do is use this reference sun simulation as magnetograms of the sun. Within these limited field of views, determine what bipole emergence is occurring or what bipoles are within these field of views. Then take these bipoles, rerun these simulations, rerun the non-potential simulations, but do that with the limited field of view data and see how well we reproduce the reference sun simulation. So the key result that we need to do, or the key thing we need to do first of all, is we need to produce a reference sun model. Now, of course, there are no bipole data sets for the sun that cover instantaneously full 360 degrees of the sun's surface. So what we have to do is generate a theoretical bipole data set, and I studied the papers by Karen Harvey and Carl Shriver throughout the 80s and 90s, where they determine statistical laws for the emergence rate of bipoles and so on. So we use these in order to produce our theoretical bipole data set. So what we see here in the image at the top left, is the butterfly diagram for this theoretical bipole data set. Just the standard features you see: emergence at plus and minus 40 degrees latitude, and then approaching the equator with an overlap of the cycle of about 1 year. Now, in this reference sun simulation, we emerged 4,770 bipoles over the 22 years. All of these emerged in this non-potential process that I described earlier on. Now, in terms of the amount of flux we emerged, it's in the order of 3 times 10 to the 25 Maxwells. If we consider the range of fluxes within the bipoles, the graph at the top on the right-hand side gives us the flux versus the bipole half separation. And what we find here is that the lowest bipoles or the smallest bipoles emerged are on the order of 10 to the 20 Maxwells, ranging up to about 5 times 10 to the 22 Maxwells for the largest many bipoles. So we've got 2.5 orders of magnitude variation in the bipole size. Now, one very important result to get the correct evolution is to make sure you have the correct tilt angle of the bipoles, so you get the correct amount of flux pushed polewards. The graph at the bottom just shows the distribution of tilt angles, which goes roughly as 0.35 times the latitude of emergence. Now, to initialize this 22-year-long simulation, we need to have some form of initial coronal field. And we choose the initial form of the coronal field just to be a potential field, which you can see here. But the key result is that the field is only potential at time t is 0. For the rest of the time, it is a non-potential simulation that we have. So, if we consider the properties of the radial field within the simulation and some of the coronal properties, then if we start the movie off, you're going to see the evolution of the radial field over the 22 years. Initially, the northern hemisphere has positive flux, the southern hemisphere has negative flux. As we start the simulation off, we see the emergence of the bipoles, we see the surface flux transport shearing them, you see the transport polewards, and then the reversal of the polar fields just after cycle maximum. We then see the activity decreasing, and then of course in the second cycle, the activity will increase again, where we see exactly the same processes. So we've compared this radial field within a theoretical data set to the properties that is observed in terms of longitudinal average of the variety of magnetograms, and this reference data set actually produces the main characteristic features that you would expect from the evolution of the surface field. The variation of the surface flux is about a factor of 4 from cycle minimum to maximum. Now, of course, the most important part for today's talk is not the surface field, but it's what is the coronal field doing? How non-potential is the coronal field? So the two bottom graphs consider this. In terms of the bottom left-hand graph, we see the volume integrated magnetic energy within the corona over the 22-year time period, and you see about 1.5 orders of magnitude difference in the energy in the corona from cycle minimum down here right the way to cycle maximum. The graph on the right-hand side represents the total volume integrated electric current, and an important result here is that while of course at cycle maximum we have much stronger electric current existing within the corona, even at cycle minimum the current is not zero, so we're never returning back to a potential field with these simulations.
A question?
Yes, certainly.
You call your total J, but it's really yes. I that you want. What is the total actual current?
So this is the volume integral of the mod of J in dimensionless units. We've not actually calculated the current in non-dimensional in non-dimensional units. So that's something that I can't really answer at the moment. But it's really just a reference point through the simulation. Yeah. Is that okay with you?
Yeah, that's fine.
Yeah.
I mean, of course, the value of the current is important.
Yeah, that's right. But of course, this is the large-scale current, not necessarily the small-scale current inside of active regions. So what we're doing here is that this is the volume integrated current over the large-scale field. But of course, this large-scale, we will be missing contributions from small internal structures of active regions and so on. So the current that we could compare to is, of course, the current that people would measure in the internal structure of active regions, but that's the current that we don't have within this. So it's difficult to compare the two of them. Yeah. Does that answer your question, Hugh? Yeah.
Yeah, thanks.
Yeah, excellent, thanks. Okay, so it's difficult to show the three-dimensional evolution of the coronal field over the entire 22 years. So what I've just done is I've just produced a static image. And in the static image, we've got it roughly 1800 days into the simulation. Again, we've got the mixture of open and closed field lines. But if you consider the closed field lines, what you generally find is that, of course, these closed field lines are sheared structures. They're no longer potential looking structures due to the presence of the electric currents. In addition to this, we do sort of get these extended cusp-like structures as well forming within the simulations, such as reminiscent of the type of helmet streamer structures that you see in the Sun. So that's the reference Sun model. So now if we move on to the limited data simulations. So what we're going to do here is we're going to use the reference Sun simulations as representing magnetograph observations. What we need to do now is consider what limited field of view we have round about these magnetograph observations, and within this limited field of view, deduce all the magnetic dipoles that are either emerging within your limited field of view for either L1 or L1 plus L5, or how many dipoles are rotating into this field of view that you can then measure the properties of at a later time. Once we've identified all these dipoles, then we can repeat the non-potential simulations just with these dipoles and compare them to the reference Sun model. So the next slide here just shows an illustration of how we can identify these dipoles. What we've got is a single day where we have 4 active regions emerging in the reference Sun model, where 3 of these active regions emerge in the northern hemisphere, 1 of the active regions in the southern hemisphere. The key thing here, though, is that central meridian on the Sun within the simulation on this day was at 291 degrees longitude. So what we now need to do is we now need to determine what dipoles are in this field of view, and we classify the dipoles into 3 separate types. The first type of dipoles are what we call real-time emergences. This is where a dipole emerges in the reference Sun model and is also within the field of view for either the L1 simulation or L1 plus L5. You can see here that on this day, no dipoles are actually emerging within the field of view from L1, so none would be included in real time. In contrast to that, due to the extended field of view having an L5 magnetograph, 2 of the dipoles which emerge in the reference Sun model would be able to be included in the L1 plus L5 simulation at the correct time with the correct properties. So in the limited data simulation of L1 plus L5, we would have these dipoles emerging with exactly the same properties at exactly the same time as in the reference Sun model. Next, though, if you only include the real-time emergences, none of the surface fields are very accurate. So what we also have to include is what we call rotational updates. This is where a dipole emerges outside your field of view, but in subsequent days it will rotate into the field of view such that you could measure its properties. So what we have to do is we have to identify all the dipoles that are rotating into our field of view and then determine the properties of the dipole on that day. We can then include these dipoles as rotational updates. For the Earth only simulation, 3 dipoles are included as rotational updates, either 1.22, 2, or 5.6 days late. Now, the key aspect here is that anytime you include a dipole late as a rotational update, you've missed some of its evolution. It has emerged on the backside of the Sun, energy has been injected into the field by surface motions and so on. You can't include that energy in your simulation. All you can do is include that dipole at the earliest possible time within your simulation and then continue the simulation on. In terms of the L1 plus L5 case, there is only 1 dipole that's included in rotational update just 2 days later. The third classification of dipoles are those which we call decayed dipoles that are not included in any of the limited field of view simulations. This is because they emerge too far away from your field of view such that they've decayed by the time that they would come around and therefore can't be included. You didn't actually know that they were there. So this slide here, which I'm not really going to go over in detail, just shows how we do the rotational updates, and we've got a model form for doing that. Once we identify the dipoles, we update the location, tilt angle, and separation based on the differential rotation profile, but we've got an analytical model constructed in a planar geometry and Lagrangian coordinates for updating the flux based on how much of the flux would have cancelled before we are able to see it. There's more details about that model in the paper. So in terms of doing this, in the reference Sun model, we emerged 4,770 dipoles over the 22-year cycles in real time. For the L1 simulation, that number drops to only 1,427. Compared to L1 plus L5, due to the extra 60 degrees view, it's now about 2,140. We get roughly the same number included as rotational updates, and of course the reversal in terms of the number of missing between L1 and L1 plus L5. So what you can see from this is that it is actually a very big data analysis problem to identify all these dipoles, include them in the simulations in the correct way. As an illustration of what the photospheric field looks like, on the top right-hand side, we see 6 bipoles that emerge in the reference sun simulation within 5 days of this time that we're looking at. If you look at the L1 simulation with its limited field of view, only 2 of these bipoles would be observable. So only 2 of them could have been included. In terms of L1 plus L5, due to the extended 60 degrees of longitudinal coverage, moving to the left in this case, 4 of the bipoles are able to be included. So this illustrates that by having an L5 magnetogram, the situation is much more accurate. Another nice way of looking at that is, what would the limb look like if we have L5 magnetogram observations when we run the simulations? So here we see the same day.
Five minutes, yeah.
Yeah, 5 minutes. So here we see the same day where we have a bipole emerging across the limb, and you can see the closed non-potential structures. This bipole emerged behind the limb is then rotating on the limb. In terms of an L1 field of view, we can't include it because we don't even know it's there. So at this location, we just have open field lines that are not storing any energy, which could be important for space weather purposes. But of course, we have these closed field lines here, which are highly non-potential. In terms of the L1 plus L5, you can see it's been able to capture this active region and the closed field lines within it. So by having that, we would be able to follow the active regions as they come around and include them within the models. So what we do to compare these simulations together is we determine a number of the global properties of the magnetic field from things like the surface flux, the total volume integrated energy, and the total volume integrated electric current. We calculate these for all 3 simulations, but then what we do is we compare the limited field of view simulations, L1 or L1 plus L5, to the reference sun model, and we calculate the ratio relative to the reference sun model. So the graphs here show the time average for each of these 3 quantities throughout the entire simulation, where the red line represents the L1 plus L5 ratio with the reference sun, and the black line represents the L1 only field of view relative to the reference sun model. And of course, if you get the true answer, the value should be 1. You can see that by having L5 observations, we are much more accurate in terms of the surface flux, the energy, and the electric current within the simulations. But what we can also do is calculate the average flux ratio value throughout the entire simulation for each of them. So generally what you find is you're 73% accurate for L1 plus L5 for the surface flux, but that drops to only 55% accuracy for L1 only. So what we find is that we get roughly a 33% increase in accuracy by having L5 magnetograph compared to just L1 by itself. In terms of the energy ratio, the increase in accuracy is about 41%, and in terms of electric current ratio, it's 30%. So that was one sort of quantity which is important, but another, of course, is flux ropes within the simulations. So within the reference sun model, in the graph on the left-hand side, we see the number of flux ropes as a function of time throughout the simulations, where at minimum, we've got 2 or 3, 4, 4 flux ropes existing, but at maximum on the order of 20 to 25 flux ropes. The graph on the right here shows again a comparison of these 3 simulations, where red represents the results from L1 plus L5, black just represents the results from an L1 simulation only. And what you find is that the accuracy level in L1 plus L5 is about 78%, but it drops to 61% within just an L1 field of view. And sorry, the cursor is obscuring my slide here, but I think it says 26% increase in accuracy there. What I should say is that in calculating these quantities averaged over the simulation, I have capped the values at 1 so that there is not this extra contamination by the values higher than 1. Here, any values higher than 1, just to note a case where a flux rope has existed in both simulations. It has erupted in the reference sun model, but is not erupted in the limited field of view simulations at that time. So hence you get a reason value greater than 1. But I have capped these calculations to 1 to take that into account. So looking at this, what I've done through this talk is I've considered what improvements could occur in global modelling if we have an L5 magnetograph. And I've done this through 3 carefully controlled simulations. What we find is that an L1 plus an L5 magnetograph viewpoint gives an improvement in global non-potential modelling on the order of 26 to 40%, depending on which global quantities you are looking at. And that, of course, is compared as an increase compared to L1 only. In terms of the overall accuracy, if we have L5 observations, that's giving us another 60 degrees, we find that we get overall accuracy of 65 to 78% of what we believe is happening in the real sun model in this case. And then if we compare that to just having an L1 field of view, it's around about 50%. So what we see here is that we do get a significant increase in accuracy just by having this extra 60 degrees of observations in the context of these models. Now, this was just a very initial study that we carried out. There are many more things that we plan to do, such as studying the number of fluxural projections within all the models, also correlating the free magnetic energy storage locations within each of the simulations, taking into account that some bipoles are emerged late because of their limited field of views and so on. But most importantly, and what's the trickiest thing to do, we want to consider the location and timing of magnetic fluxural projections throughout the simulations. In particular, particularly those ejections that occur within plus and minus 60 degrees of central meridian, which of course could lead to CMEs that impacted on the Earth. And we want to see how much better the L1 plus L5 simulation is in reproducing these compared to just having the L1 case by itself. Okay then, so thanks for listening today, and I'll just stop there and get any questions.
Okay, thank you very much. Very interesting presentation. We open for questions. Please go ahead and mute your microphones if you have one. Meanwhile, I have a question. So you described how much improvement you could expect if you add more data, more observation. But in addition, you could consider how much improvement in principle you can achieve algorithmically with available data, because still your models are simplified and non-perfect in reproduction, what you see.
That's right. So there was a study carried out by Gordon Petrie and Alexei Petsov and I think Mark DeRosa, where they incorporated observational data and used the synoptic magnetograms in order to produce sort of synoptic magnetograms that would occur by having both L1 and L5. And they also looked at what improvements you could get from that. The key difference that I've got within my simulations is that I need to run them as continuous long-term simulations. So I can't ever be resetting the surface field based on observations, because if I reset the surface field, then the coronal field's no longer consistent with it. So I then have to reset the coronal field back to potential. So that's something I don't want to do, because really I want to be studying the non-potentiality of the corona. So, but both methods are, very applicable methods and correct methods to go forward and use in these studies. Yeah.
Mm-hmm. Okay. Do we have more questions, please? Okay. Everyone else is muted, so that means that we do not have any other questions other than you had a few during the talk. So if not, so thank you very much. And the next talk, if I remember right, is by Dana Longcop in 4 weeks. Thank you very much. Goodbye.
Thank you, Gregory. Thanks. Bye. Bye.